I'm already on record. Doing it all day.
Okay, what you have, John? Yes.
Can you give us some just general sections that you think are most important before I ask any very specific questions? I know that it's like the whole class from start to finish.
I mean, I know the zero theorem. I know how to, decompose billion groups. Yeah, I hate answering questions like that because, I kind of freestyle it when I make up the exam. You don't really think about it from that point of view. But, know what ideals are, know what
Yeah.
kinds of ideals, especially the commutative algebra. I'm not saying I wouldn't actually something non-commutative, but, that's probably mostly where it's going to come from.
Doing definitions.
Yeah, know all that kind of stuff, right? And definitions, of course, they don't have to be word for word, but they have to be accurate. Right? So,
A couple of just quick clarifying questions. So, theorem 5.3.12 states, if we let R be a commutative ring such that R squared equals R, then any maximal ideal of R is prime. Now, is the distinction between that, do we only get that any maximal ideal is prime if we're in a commutative ring with one? Is that the distinction? That this is a sufficient condition if we are not guaranteed to have an identity?
I think what you're saying is, yes, this is a generalization of a ring with identity. And this generalization is good enough for maximal to imply prime. So in particular, if you have any commutative ring with identity, any maximal ideal is automatically prime, but you can loosen it a little bit to this.
Okay, that's great. And then after that, there's a remark here and there's a remark in the PDF which has this list of implications, starting with if R is commutative with one, then M is maximal if and only if R mod M is a field. If and only if R has no non-zero proper ideals, which confused me.
Well, let's make sure that there's not a typo there. So what does it say, R?
R and I should probably look this up in the PDF as well, but actually I'll just look up exactly what it says in the PDF, but I'm pretty sure it was equally confusing to me.
Do you know what number theorem it was?
It was it's a remark right after 5.3.13. I have it
So
here.
5.3.13 is the one that you just put there. It's a little bit different.
Yeah.
Oh, they're out of order. They're out of order in I think we got a different order in class than we did,
Yeah.
It could be, yeah.
but there's a remark with a bunch of implications.
It should be noted in tandem with the above theorem, and in particular, as far as commutative identity, that M is maximal if and only if R mod M is a field. Okay.
I'm good with that. If not, R mod M is a field.
If and only if, what's next?
Oh, I see.
R has no proper ideals.
And R is a field if and only if R has no proper.
Yeah, I think
identity.
And R is a
they're two
field.
separate
Okay.
ones.
Okay, and R is a field
I
if and only
see.
if R
That
has no
was-
proper ideals.
That's
Okay.
was that makes sense. In my notes from the class, I had RM is a field if and only if R has no non-zero ideals, and I'm just like, I don't think that's true.
Right. Yes, no, I wrote these notes a number of years ago, just patching things together, and I'm still getting typos out of it, so. Okay.
And one more little thing.
Sure.
So as far as unique factorization domains go, we had two equivalent definitions, and we touched upon it briefly in class. But the first and the second seem, the first seems strictly stronger than the second. In the PDF, I think the first and second, A and B, are actually identical in the PDF, but in our notes, I believe we gave that if you had two irreducible factorizations which were equal, that implied they were the same length, and they were the same up to unity.
Right, so.
Was the first one. And then the second one was if you had two irreducible factorizations of the same length.
Mhm.
Then
you compare off the factorizations. Yeah.
right, how is the latter not strictly weaker than the former?
That's beyond the scope of this course.
Okay,
Yeah, that's a hard thing. I put that in there for fun, but you're right to look at it. The first statement is, the second statement is a weaker statement, right? Because the first statement, so let me make sure we're talking about the same thing. So in statement one, you have irreducible factorizations, pi one, pi two, pi n. Yeah. Then that's the first statement, that for unique factorization. The links, if you have two irreducible factorizations that are equal, then they're the same length, and then you compare them off. Second statement is this. If you have two irreducible factorizations that are assumed to be the same length in the first place, then that's all you need, right? And see here, you assume that they're the same length right out of the gate. This is on the surface of it a weaker statement than this one, but they are in fact equivalent. And that is very non-trivial, right? I just put that in there for fun because it is actually, and actually this theorem, unique factorizations are 150 years old at least. And this theorem is like 10 years old or less. So.
Question. So this is from section 2, just on ideals. We define two ideals added to each other, I plus j, and then two ideals multiplied,
Right.
I times j. And when I was looking for my notes, I couldn't tell if both of those were supposed to be ideals themselves.
They are, right. And so like they look a little different, right? This is equivalent to, this is the ideal that's generated by the entire set I, U, and J. So just take everything in I and J, throw them together, and see if they generate these, and you can shortcut it to this. No way this is going to be an ideal by itself, because if I have alpha 1 times beta, and then alpha 2 times beta 2, there's no guarantee I can revamp that as a single alpha times a single beta. And so to get around this, you have to add them. When you do projects, you have to add them up. There was actually some papers written in the 90s or early 2000s about ideals where under what conditions can you take an ideal like this and write it just as a single term and forget about the sum? And it's pretty rare. It's pretty rare. For example, a principal ideal. If both I and J are principal ideals, you can do it. But besides that, it's pretty rare.
And then my second question is about the zero-dimensional and one-dimensional rings. Because I know we used like zero-dimensional when I was looking back through the homework. I just feel like I found different definitions for things, so I wanted to like, and I don't think we ever really
If I can
defined.
screw anything up, they should all be equivalent, but we can go
Okay.
through. So
I don't know if we ever defined like dimension for rings.
we may not have, but I'll do it, yeah, because I'll probably only define 1 and 2 dimensional just for specific problems. But I'll do it in general, and that might create an easier picture.
Okay.
We say the chain of primes of R. We might as well make this strict, so we replace our own time. Is a linear. So we actually start counting with 0. Right. And so you can define something called the dimension there are different kinds of dimension that you can define. Kroll dimension is the most common and most used, but some people want to be really specific. All this is over n such that there exists a chain of primes. Now you can go a little bit further and start talking about what Kroll dimension is, countably infinite or uncountably infinite, so on. But basically, okay, this is what I'm going to tell you is actually sort of incorrect, but paints a good picture. It's sort of how high you can stack your prime ideals, right? That's basically it, because you look at all, notice that I've stacked them in high here. You basically look at all possible stacks of them and take the supremum, and that's what we call a Kroll dimension, right? So, yeah. So this bounces back into homework. So if your dimension is 0, that means that you never can stack more than one in a row, so all primes are maximal. All right. If them are 1, then all chains look like 0, 4, 0. Because you can never stack it higher than 1 high. Right? So if then always P0 is going to be the 0 ideal. Because if you're in an interval domain, 0 is a prime ideal and it's contained inside of every ideal, right? And so R is a 0-dimensional domain. R is a field. If R is a 1-dimensional domain, then R is that, then all non-zero prime ideals are. Are max. For example, Z, where your primes look like this. That's what all the stacks of primes look like. Always 0 at the bottom and then generated by non-zero prime at the top. Or in fact, any PID. And in fact, if you encounter a ring, more than likely, if you encounter a ring in a number theory course, it's very likely its dimension will be either 0 or 1. If it's 0, it'll be a field, and if it's a ring of algebraic integers, the dimension will be 1. It just means that all non-zero prime ideals are maximum.
I think, so on that homework, I kind of said that it has to be at least one dimensional. Is that like an okay way to argue that, like, if all prime ideals are maximal? Then it either is one dimensional or it's a field. Is that like,
If all prime ideals are maximal, it has to be zero dimensional.
oh,
If
all
all
non-zero,
prime-
non-zero.
Well, if all non-zero prime ideals are maximal, then it's, well, it's either a zero or one dimension.
Okay.
Are you saying? So I think for the homework, we could argue, because we were trying to show that any PID is the same as a UFD, which is zero or one dimensional. Because one dimensional is zero dimensional is strictly stronger than one dimensional, right? We could have just argued for one dimensional and said,
Well, the zero dimensional is sort of degenerate because you've got a field.
right. So we really just wanted to show it
Do you want me to go through that?
one dimensional.
The, okay.
Again, I
Was
wouldn't be upset though.
Well, which problem are we talking about?
It's like
Show
the
that
very last one.
a
2D.
principal ideal domain, if and only if it's a unique factorization domain, which is of dimension less than or equal to one.
Okay, I think I
Is
can
that the
prove that
last
pretty
one?
fast.
Yeah.
So it goes to-
Let me ask you a question, so you can think
Yeah.
about this while I go through this. So notice that the length of this is, you know, how the length of a particular chain is how high you can stack. You know what it means to be Noetherian? Right, every ideal is finite generated, but it was first defined to be the ascending chain condition ideals. Is it possible to have a Noetherian ring that's infinite dimension? So think about that. I think we did that actually in class, because to give a PID, show it's a UFD, you have to show that every non-zero prime ideal contains a non-zero prime element. But every non-zero prime ideal in the PID is generated by a single element, which is prime, so, okay, right? And we need to show that the dimension is less than or equal to one. So suppose we have suppose we have zero inside P1 inside P2 in our PID. This is correct because it's PID. Notice that and as x prime and not zero, x is irreducible. But R is a unit. Because one of R and Z has to be a unit, and it certainly better not be Z, otherwise it generates the whole ring, and it's not a proper prime idea. Therefore, the ideal generated by X is the ideal generated by Z, contradiction. So its dimension can never be any more than one. Okay. So that's one direction. The other direction is suppose R is UFD and suppose that P is the non-zero prime ideal, say. Then there exists non-zero prime P and P. Right? Therefore, we have 0 but R is one dimensional. Right? Or zero dimensional, but if it's zero dimensional, then all this crap is zero. It's a field. Therefore, these two must be equal. This is a prime element, so it generates a prime ideal. It has to be this whole prime ideal here. So every prime ideal in R principle. So R is infinity. And that was the significance of the problems before that, because we need that last step there, that every prime ideal principle is good enough. So what do y'all think? Can you build a Euclidean ring that is infinite dimensional? Well, let me tell you what you can't do. You can't make that stack infinite, because that would deny the ascending chain condition.
Oh, but it's the supreme.
It's the supreme. And you actually can. It's a terribly interesting construction, but there's a lot of details to be shown here. But let me show you how to do it just for fun. Just something fun. Pick your favorite field and adjoin variables look like this. So notice I've stuck on countably many polynomial variables indexing this way. And I'm going to think of these in clumps here. But P1 collect these prime ideals like this. Let me point out that this is prime because when you mod this ring by that, it's just essentially killing that variable, and it's still in the domain. When you mod out by this, it's essentially killing just these two variables, and it's still domain, and so forth and so on. Now, you're going to love this. Let S be let S be the set complement of a union of these primes that we've created. And let the domain T equal R localized S. Now the correspondence theorem tells us that the only prime ideals left over in this are the ones that miss that set. And the only ones that miss that set are the ones that are contained in these primes here. So the primes in here correspond primes contained in so let me show you what happens here. Basically, in the ring T, primes look like this. And then, right. Actually, there's more primes because you can also go to an intermediate X22 and up here, and it's much worse. There's also x21 plus x22 that's in there, but this is just a representative sample. We also get x31, x31, x32, inside x31, x32, x33, I1, I2, I3, et cetera, et cetera. Right? How do you know it's Noetherian? Because all the primes you used are finitely generated. Right? And that was one of our characterizations. Now, that's really fast and loose because you might say, well, how do you know that one of these primes can be done? In here is not finitely generated. There are things to prove here. But this is a terribly clever construction where you basically build the stalks of different height and you guarantee that you keep it Noetherian by making sure that all your maximal prime ideals, which correspond to these things, are actually finitely generated. This is an old construction due to, I think, Nagata from the 50s or 60s, something like that. By the way, I have gotten, you all are done all the way through 13, and I should be able to polish off 14 tomorrow. I actually had more traffic in my office today than I thought I was going to, so there you go.
So the final exam will cover everything we'll talk about, right?
Yes, it will cover from the beginning. It's comprehensive.
Are we gonna talk about like the theory and stuff too? Like,
You should know the definition, right? I'm not gonna ask you theoretical stuff. I mean, I talked about it for what, 15 minutes. You know.
You should be able to do something like this that he just did.
Yeah, that's right. Just do this from scratch.
Yeah, 2.5 hours.
On the correspondence theorem there, I'm just wondering if you could talk a little bit about like well, okay. I always get tripped up when we go from localizations of just like an ideal or of a set to localizations of a prime ideal,
Okay.
because that notation always like, because I don't know if it's a specific example, I don't always see right away that that ideal is prime. And then it really messes me
Well,
up.
so for example,
But then that it connects to the correspondence there, so.
let me start with something small. So for example, if you look at the, and let's see prime ideal, the ideal turns. That's certainly prime ideal. What you do here is you take the multiplicative set to be everything that's the complement of this, right? So this looks like fractions like this, where so you're allowing denominators as long as they're not multiples of 3.
It's
Right?
not 3 divided by b, it's some a.
Yeah, because what I want is I want B to not be in this item. So I want the GCD of 3 and B.
And then a can be any integer.
A can be anything. Right. The numerator can be anything in the range. And so notice that there exists a one-to-one correspondence ideals of Z that miss S. Prime. And also the ideals are that form too, but so in the way this works, and this translates, what does it mean for an ideal to miss S or a prime ideal to miss S? right? Because here's what you did. Here's the integers. And here's the ideal derivative by 3. All the multiples of 3. What you did out here is you turned all the outliers here, all the stuff in S into units. So the prime ideals that miss S, to miss S, it's got to be contained in here, right? And so actually, there's only one prime ideal, the integers. No, I take it back. There are 2 prime ideals, the integers, that are contained in the ideal derivative by 3. The ideal derivative by 3 and the 0 ideal. And so you've gone from something, the integers, that has a whole bunch of prime ideals, into a simpler ring where the only ideals in here are just 0 and 3, actually generated by 3. It's also generated by a single element, just like the other one is. It's just you've got more things to multiply. Yes.
So if our ring is one-dimensional, then whenever we do this, our P is always going to have only one prime ideal.
No, not necessarily. So
It's a
for
domain.
example, let me give you an example. This is what localization can do for you. So suppose you have a complicated ring here, and all these primes here, P1, P2, P3. This Q, this PM, something like this. Right? If you look at our localized P1, the only primes that survive are the ones that live inside. Oh, and here's the 0 ideal. Better look inside all of them. Just call it 0. The only prime ideals that survive are the ones that live inside of P1. That is, that miss the complement of P1. So RP1 will look like this. All this stuff turns into units now, right? Stuff in Q can be used in the denominator. Just like in this one, you can use 2 in the denominator now. Right?
Is what you have drawn there, is that one-dimensional?
No, absolutely
So
not.
is that not?
And let's assume, just for the sake of argument, that these are the only prime ideals in the ring. This is 4-dimensional.
So basically he was asking if one-dimensional.
No, he asked if you localize it a prime, it's always 1-dimensional.
No, I said if R is one-dimensional, does that imply that RP only has one prime ideal in it?
Technically, no, because are you localizing it a non-zero prime?
Yes.
Then it'll have 2. It'll have the
And
non-zero
not
prime and
zero.
0. Yeah,
Yes.
it'll only have one non-zero. If you localize it 0, it'll be the quotient.
So, yeah, that's what I.
Oh, okay. I have a question. So then if you, it would it be correct to say that the prime ideal you localize at becomes the maximal
It
ideal?
would be absolutely
in the neighborhood?
correct,
Okay.
because, so P, localized P is, in fact, a unique maximal ideal of our localized.
Okay, that makes sense.
Yeah, and you see that mess I drew up there, it's kind of a neat trick, because you got to get rid of some of the noise. If you want to just, if you don't care about these problems over here, because they're just making a mess for you, you can localize.
You
Yes.
said P, localize it P.
Right. So P localized P.
I'm a little confused now. Is that a P itself?
This is the set of P over S. P is in P, and S is not in P. Right.
Okay,
So it's just like our localized P in the sense the denominators are not in P, but now the numerators are forced to be in P.
That's a fun definition.
Yeah.
PP equals P times R. P sucks all the numerators in the P.
That's right. And notice it's kind of interesting because notice these are precisely the elements of R that are not invertible, right? Because if your numerator in RP, this is the set of R over S, where S is not in P. What does it mean to be a unit? It means you can invert the fraction. And what does it mean to be able to invert the fraction? You need the numerator to not be in P. So this is precisely the set of non-units that we're in, stuff that you can't invert.
The 9 units of RP, not of R. Or the 9 units of R.
Yes, these are, I'll be careful here, these are the non-units of our local estimate. Okay, so I'm gonna try to keep my eye on the chat. I don't think I can hear you guys out there, which I don't know what that's all about, but at least you can type in. Okay, so I've got a question here from Colin, and thank you for your patience here. By the way, here's what I'm gonna do, because I get all excited about stuff. So this is a good way around it. I'm gonna put my cell phone number in the chat, so at least it'll jingle or something if you guys have a question. I haven't gotten back to it. There you go. My cell phone number. Put it in your phone. It'll be the only North Dakota area code you're fun. So don't ever say I never gave you anything. So we have a question. Let's see if I can. It's right here. 3, 6, 7. Minus 12x5. Plus 8x4 minus 240x plus 2. Then ZX. We can use the rational root test to find possible roots. How can we show that none of these are actual roots? Oh, I know a quick way. I know this polynomial here it is. You know, yeah. This polynomial. This is 2 Eisenstein, right? I think that's right, because I think 2 divides everything in the square, this doesn't divide this, and 2 doesn't divide that. So this polynomial is in fact irreducible over QX. And in fact, since the GCD of the coefficients is, it's actually even irreducible over ZX as well. For this to have a rational root, there would have to be a linear factor, right? There would have to be a linear factor for this to have a rational root. So, no rational roots. Now, if you didn't know it was 2 Eisenstein, so for example, if you didn't have the criteria, the possible rational roots would be that's a terrible notation, but what I mean is it's any possibility of these for the numerator, these for the denominators, right? So I guess you'd have what, 2/3 plus or minus, and you'd have 1/3 and 1 plus or minus. Those are the only possible rational roots, and you could go through and try them, and they either work or they don't, right? But Eisenstein's easier because nobody wants to plug in 2/3 of this crap, right? Sure. Everybody okay with it?
Can you just say the thing you said again? If it did have a root, it would have to be a linear factor. How did that work?
Right, right. So if this has a rational root, that was one of the theorems we had about polynomials. So if, let me call this something like f of x. If f of r is 0, then f of x is x minus r times whatever you divide it through by.
Mhm.
Right? And so in particular, it would have to reduce.
Oh, I see, okay.
How did you get that it was 2 Eisenstein?
Because 2 divides every coefficient except for this one. Right, and it doesn't divide this one, but you also need that. And the square of 2 doesn't divide this. So that means it's 2 Eisenstein. Right? Now, if I change this to a 9, you totally goes.
Okay.
Right, because it's not anything Eisenstein.
Okay.
Would you be able to just work through a quick problem from homework 13, just so I can see your process for dealing with the
Sure.
half factorial domain, or it's like the.
Oh, which one was it? Z, which one?
It was asking to show, yes, that z square root of -14 is not a half factorial domain. I like when things become concrete, not, sometimes I struggle.
Okay, so basically what I gotta do is show a couple of factorizations at different lengths, right? And a tool that I'm gonna need along the way. Got this norm map, and remember it had some properties that like norm of x is 0 if and only if x equals 0. Norm of x is plus or minus 1 if and only if x is a unit in R. And well, wait. Remember all these properties? And actually, for this particular application, you can change this to norm of x equals 1, because no way is this thing ever puking out a negative number. Never gonna happen, right? Always at least 0. So, we take a little break and we play. You play around with some elements here. But so for example, notice that now I don't know much, but I'm guessing these are all irreducible. This certainly seems to indicate it's not a UFD, but it's not good enough for an HFD, because it looks like, unless I can break this down further, which doesn't look like, then, so I need something with a little bit bigger, that breaks down. And actually, I'm going to sort of use the norm again, if you like. And by the way, I'm going to come up with an example that I think is pretty economical, but there's infinitely many examples like this in here. What do I want to do? How about this? That's right. +25 + 56 is 81. And this is 3 times 3 times 3. By the way, you can get that just from kind of playing around with this. In fact, you can do it with 14 if you're big enough, I guess. Like, to make it interesting, like what's 14 plus some squares, right? Well, actually, you might be able to do it this way. You might look at 2 plus radical 14, 2 minus radical 14, and that's 16, which is 2 times 2 times 2 times 2. That might even be easier to do. But see what I did with b equals 1, I just add some squares to it and see if I get something with a lot of factors. That's kind of what I looked at. I started with b equals 2, that's 56. You add 25 to it, 81, lots of factors. Right, but there's, like I said, I think probably, yeah, that should work. 4 and 4. Oh no, not 2. Yeah, 4 and 14. 4 and 14 is 18, which is 2 times 3 times 3. Yeah, 2 plus radical 14 should work as well too. It doesn't give us a dramatic example. You'll have 2 irreducibles that equals 3 irreducibles. But there's a lot of things you can do. Now, hear me now and believe me later. These are irreducibles. And if we convince ourselves that they're irreducibles, there, I've got, but it's not an HFD, right? Because I've got one that's 4 length, one that's 2 length. Okay, so let me tackle this. How do I know that 3 is irreducible? There's something to be supported here. Well, I'm going to use this norm. Suppose I can factor 3 into 2 non-units, right? I don't want to waste my time factoring the units here. And by the way, let me give you another kind of cool thing about this. How many ways are there to make this equal plus or minus 1? How many ways can you think to solve the equation a squared plus 14b squared is 1 or negative 1? Well, no way to do a negative 1, right? No, because pluses rule out. B has to be 0 for sure. Agreed? And now you got a squared equals 1, and a is an integer. So that's it, plus and minus 1, and that's it. So the only units in this one are just plus or minus 1. So it's easy to tell. So this is actually, if this were a squared minus 14b squared, it's more problematic because I promise you, you will get non-trivial solutions to that. Let me see if I can get you one real quick. 6, 9, 6. Oh yeah. I guess 15 squared, which is 225, minus 14 times 16, which is 224, is 1. So you'll actually, if you replace a positive by a negative, you'll have infinite solutions, as a matter of fact. But here it's convenient because the only units are a plus or minus 1. But I'll go through this. So those 3 can be broken down into non-units. So it's not an irreducible. That means that the norm of 3 is the norm of alpha beta. And the norm of 3 is 9. Now, if you want to break this down, think about what we're doing here. These 2 suckers are integers, and they're positive integers, at least non-negative. And the product has to be 9. Both of these are stupid because they have a 1 in them, right? Which would mean that one of these is a unit. I didn't want that. So the only way that you can break 3 down is into 2 elements, both of which that have norm 3. Now, and that's insoluble, right? Because again, like you argued before, Sydney, you need b to be 0, otherwise you're way too big. And once you got b equals 0, you're stuck with the equation a squared equals 3, which is not solvable in the integers, right? So no way, no how, 3 is irreducible. Agree? And some of these too as well, but it's a little harder. I'll go through the details for one of them. Let's suppose that so that means that the norm and this turned out to be 81, is norm alpha, norm beta. And let's kind of go through this again. Again, we have positive integers here. Their product has to be 81. There's only so many ways to do this. And then everything else is a repeat of what we've just done, right? Do I agree with that? This one's the ridiculous one again. Right? This one's not possible. Because even if you've got an element of norm 27, you still don't have that element of norm 3. We already showed that. So even if you could get a beta of norm 27, there's no alpha to help it out. Right? So can't do this one either by work we've already done. So that means that you need norm of alpha to be 9. And here we'll write alpha is x plus y radical negative 14. Well, with this one here, let's see what we got here. Is x squared to y squared is 9. Now that certainly is solvable, right? But there's only, well, there's only 2 solutions. Again, y has to be zero. And so I conclude very quickly that the alpha must be plus or minus 3. But this does not divide. Very plainly, it doesn't divide this because there is no 5/3 plus 2/3 radical negative 14, right? Right, okay with that? And if you want to be really fancy, the act of changing that plus to a minus, maybe you might have done this in the homework, is actually an automorphism of this ring. And so if this is irreducible, so is its automorphic image. But the proof that the minus one also has no irreducibles is exactly the same. Okay, any questions on that?
I have to proctor at 7. Is there any way that you can record the Zoom meeting so that I can see?
I
like,
think
the
we're
rest of
recording
the
it. Please
review?
tell me, yes, we're recording it now.
Okay, perfect.
And actually, I've got Collins out there directing my camera, and he's like up there with Stanley Kubrick, I could tell you. So it ought to turn out really good.
Okay, perfect. I just have to proctor it at 7.
Actually, that remark probably means that for a 2-hour review session, you'll have like 20 hours of film he's got to cut. So.
I can't find it right now, but I had a comment on my homework about where the student's orange on one thing, and I had a chain. And you said something earlier about it being.
You assumed it
countable.
was countable, right?
Yeah, and I don't, how would you fix that?
Just by not putting integers there, right?
Oh.
So,
Don't figure out that box, you do it really person.
yeah, because, so I picked on a couple of you about that, so don't feel all alone, because you said something like, okay, you have this chain, I is contained in, I think you said J1 maybe.
Yeah, J1, J2, and whatnot.
But see, a chain, all that means is that it just means it's a totally ordered subset. It could very well be uncountable. Right, and so it's a little thing, but I wanted to bring your attention to it.
So I was looking through the notes, and one of these things we showed that any Euclidean domain is a PID,
Mhm.
and we didn't do that in class. And in the notes, it literally, it like has a thing, and then it just says, it's easy to see that X generates I, where X is an element in.
You want to go through that, you want me to show that the Euclidean domain, yeah, the proof's not too bad.
Yeah, because I just don't like, I don't see why that's clear that X generates I.
Okay, so let's go through it.
I still do not, it's not, like, this, I said this is that, right, so shouldn't that already be this would be that?
No, because that could be uncountable.
Oh, this is not the way I want to do it. No, that's correct. But yeah, and that's okay, that's okay. You want it to be uncountable? Right. Be careful that she does not.
Right, your chain might be countable, but it might not be.
Do we want it to be countable? It could be either.
Well, it could be anything. The problem
Hold on
is,
a second.
so what you have,
Does it matter?
I promise I'll get right to
I'm
this.
sorry.
So-
Which question do you send you? I don't know. if you-
No, I'm still trying to comprehend why
I was. just
How-
asking,
like, how would I
can we
write
show
it
that
that
immediately and domain is-
it's good. Do I want it like, okay, so it's either
Okay,
countable
so
or uncountable.
remind me what you're proving again, so I'll put it in the right
I'm
context.
trying to show that every chain has an upper bound, but I just had chain.
Right, but what is your set in the first place? It's a set of all ideals that contain your balances.
I had J alpha such that alpha within the index. That's your chain though. That's my chain. What's your original? That contain I. Such that the intersection of S.
J
and M.
containing I such that what? J is not principal or something?
J intersect S is empty.
Okay, J
Yeah.
intersect S. Okay, so let me take you through this a little bit. So this is maybe called this gamma. So this is just a collection. Notice that I is in gamma. So not the intersection, right?
Yeah.
And this set is partially ordered. Oh, by the way, before anybody has to go, make sure that you ask a question. If you got to ask a question, you got to get out of here. So here, this is a chain. This is my chain.
Yes.
And I know I'm used to thinking of countable chains too, but there's no reason to suspect this is. This index set may be finite or maybe incountable.
Could be.
Right, it can be humongous, right? And this is just, and what does it mean to be a chain? All this means is if alpha and beta are two indices here, that is, if I jerk two of these out at random, the J alphas contain J beta, or J beta and J alpha. And so if I wanted, and what you want to do is build the union of the chain, right? Just do this. Like that.
So just avoiding using the natural number.
Yes, right. So like the little blue light special went off my head when I saw the index chain, index of the end.
Okay, I get it now. Okay, yes.
Before I run, are you just gonna
So
introduce
I
some
put a
minimal
one and a
element
two
to show
there.
that R has to
And
be
that's
zero
what I
in
don't want.
the
I want just like alpha,
definition from
beta.
the Euclidean
That,
domain?
that's essentially it, right? You take the ideal, you assume it's non-zero, take the element in there, smallest Euclidean.
Yeah.
norm.
I just want countable, that
You can
is,
show
I
that
like
generates,
countable.
by showing when you divide it.
I did the
the
same
remainder of
exact
zero.
Right.
Yeah.
Awesome.
I get it
Thank
now,
you.
okay.
Sure.
All right, well, thank you very
I
much.
was-
I will see you Thursday.
Sounds good.
See you guys.
Okay, so let's go over this. So apparently I like really sort of waved my hands at this one and never really proved it. So we'll prove it. Let R be a Euclidean domain, show R is a PID. Let me remind you those quick so that I've got the tools right at hand. What it means is R is a domain equipped with a function, usually called the Euclidean norm, from R minus 0 into, well, some discrete subset of the integers. Such that, I think I can find it this way. And B, divided by X. And we apply QX with R0 or strictly less divided by. So what it means to be a Euclidean domain is basically basically you've got this little division algorithm like you used to in grade school, where you can divide something by 19 and get a little remainder that's smaller. Right, that's kind of what's going on there. Now, it turns out that any domain that has one of these Euclidean algorithms that performs this way is automatically a PID, which I think is like really interesting. It's actually much easier to show this than it is to show that a PID is good. In fact, that requires choice. But let's do this. Would not be a non-zero ideal of R. Any non-zero ideal you want. Look at yes, column. Look at phi of A, this Euclidean norm function. As you run through all elements, all the non-zero elements, the ideal I. Notice that this is a subset for the natural numbers union 0, and it is not empty. And I wish I'd used a different thing back. Not empty. Because I know that the ideal is non-zero, right? And that was a slightly important assumption. Right? Now, I don't know much, but I know that every subset that's not empty of the natural numbers union 0 has what? A minimal element. That's actually equivalent to induction. As a matter of fact. By the way, I don't claim that X is unique. I just said pick one of them. Be any one that has minimal Euclidean function. I claim that that is the case. And once I do this, of course, I'll be done because I've shown that an arbitrary non-zero ideal is generated by a single element. Notice that X is an element of I. So that contains easy peasy lemon squeezy. The other one that I is contained in the ideal generated by X, that's got a little more oomph to it. This is where we have to use Euclidean. Okay, so run the Euclidean algorithm. Notice that R is actually an I, right? Because that's an I and X is an I. So this linear combination, namely R is an I. So phi of R less than phi of X is impossible. Because X was selected to have minimal Euclidean function. Therefore, R must be 0. But if R is 0, then alpha is QX, Q times X, which is in the ideal generated by X. So Y is contained in the ideal generated by X. And there you go. Yeah.
Is Q,
Was that not?
is Q and I?
Not necessarily. It's just the quotient that you get here is just, it's just some other element of R. Let's see here. For n greater than or equal to 5, measure A in minus 1. Proper subgroup. A in maximal order. Let's see. So we got a question. We did say greater than or equal to 5. That'll help. Anybody know how to do this? So, I think it's not true for 4, right? Because A4 has order 12 and A3 has order 3. Right, but A4 actually has a subgroup of order 4, which is too big. Yes.
I have a clarifying question. What does the subgroup of maximum order mean?
Well, let me make sure I got the question wrong. It means there is no subgroup of order AN that's bigger, has a larger order.
That is not equal, right? Oh, okay, yeah. I said, yeah.
Right.
That makes sense.
Right, so notice this has order n minus 1 factorial over 2, and it says n
Right.
factorial over 2.
Okay.
Okay, so suppose K. Let me see how this works out.
I know.
Suppose you have a subgroup of, yeah, and again, like I said, it's kind of interesting. This is right. That's work well. It says a subgroup. Oh, yeah, you need that greater than or 5. So suppose you have a subgroup K, and K is of greater order than this, and is a subgroup of AN. Well, notice the index. Let's call it little k, is less than n. Correct. And I think I've got that. Because this means, let's let L set of left cosets. Okay. I'm sorry, of AN. Oops. And notice the number of left cosets is K, correct? Because it corresponds to the index. Let AN act on L left translation. And let me remind you what I mean. If A is an AN and let's say GK is an L, so there's a left coset, then A acting on GK is AG. Everybody cool with that? This action gives produces a homomorphism phi from AN into SK.
That's a little bit, right?
Yeah, and this is the symmetric group on K things, right? Because basically each one of these commutes the left cosets, right? Now note that the kernel of phi is not equal to AN because well, in fact, because K right is a proper subgroup. Right, think about what it means to be in the kernel. It means it has to fix everything, and since this is K is a proper subgroup, it's not going to work. So the kernel is not equal to all the way in. Yeah, so here's a quick example to kind of justify this. If K is a proper subgroup, then there has to be a GK that's not equal to K, right? If the kernel is all the way in, that means that one operating on this, well, let's see, is that what right. So I guess the way to do it is operate on K. So with A not being K, notice that A operating on K is AK, which is not equal to K. And so the kernel can't be all the way in, right? As long as K is a proper subgroup, it has to move. There has to be something that moves K, so the kernel's not everything. And let me point out that the order of AN is n minus, is n factorial over 2. And the order of K let's see.
Did you see that?
I need something else here. Oh, it's SK. N factorial over 2 is greater than or equal to n minus 1 factorial if n is greater than or equal to 5. Right. But notice, for example, if n equals 4, this is 12, and let's still work here. What have I been wrong here? En. See, this is 4, it's 12. Still work, shouldn't it? Hold on a sec. See, A3 has order 3. A4 has order 12. It's got 7. in this case would be Huh. Here, let me, there's something about this that's bothering me. My proof is seeming to work, but let's see, the statement of problem, let's see, for n equals 4, A3 has 3 elements in it. A4 has 12 elements, but it's still got a separate for 4, which is bigger than A3. So what happens here? This should be 12 into 1 into 8. Oh, yes. You need A5 for the simple. You don't need it for this. This is actually true, I guess. I see where I was going. Let's see. 6. Yeah, this is actually true for all n greater than or equal to this inequality. And this is greater than or equal to k factorial, which is your SK. Everybody agree with this? So if n, in fact, is greater than 5, greater than or equal to 5, then B, well, let me put it this way. So if, and it's a tie here, isn't it? 2 factorial of 2, no, it's not a tie. So if n is greater than or equal to 2, then phi from an into sk cannot be 1-to-1. Agree? Because basically this thing is always bigger than this. And even for 2, it's strictly bigger. 2 factorial, no. Greater than or equal to 3. It is a factor 2. Agree? But if n is greater than or equal to 5, an is simple. And there's your contradiction. Right. And so, right, A4 is not simple, but A3 is simple. So this should work with 3 as well. Okay. Everybody, any questions on that?
I'm just trying to remember a lot of things here. So AN is simple means it has no
Non-trivial,
non-trivial normal.
normal subject, right?
Okay,
And
so
so-
here then SK would be,
Right. So here, what we did right here, by making this remark, we showed that the kernel cannot be all of AN. That's all it takes. This remark right here shows that the kernel can't be just the identity. That's now all it takes,
oh, okay,
right?
okay,
And this throws everything out in the case when n is not 5, because so the kernel can't be everything, and it can't be trivial, right? So the kernel has to be non-trivial, but that contradicts the simplicity of AN. Any questions?
So AN is simple, it finds something.
Right.
details like that that I can't remember.
Right.
Yeah, this one is like, I mean, more flashbacks on that homework.
I just need to go review a couple like
Yeah,
action proofs.
I messed up on the midterm exam for that because I accidentally got my numbers wrong. I was like, dang it. Like I wrote them. Are you going to be available tomorrow in your office at any time?
You're not gonna like my answer to that. I'll probably be here from about 5 to 7 in the morning.
Oh,
Uh,
okay. When do you sleep?
Well, who knows? Maybe I'll be asleep in my office. No, I'll, because I get my test done on Tuesday. You know, back we only have to get tested every other week, but I was like, if I don't get tested every week, I'll just forget it and then I'll get in trouble, you know, so. But yeah, so I will be here. I might be here in the later afternoon. So if you're in a spot, send me an email. I'm gonna be working at home, but then I've got another review session for my linear algebra class. It starts at 6, I think, so I'll probably roll back up here at some point.
Need a refresher?
Yeah, because tomorrow is when I'm gonna start doing problems, and so I probably won't be even ready to ask questions for it now.
I'll be up here Wednesday early too.
Okay,
So, and you know,
I'll be here all day on Wednesday, because I have an exam.
and yeah,
today.
I mean, I guess you guys have figured it out, but just in case you haven't, my office hours are the same as they were. But that block when I usually have classes, I'm free now, so I'll just be sitting up here doing work, so.
I just checked it.
Okay.
The homework 13 that you just graded.
Uh-huh.
Let's see. Thank you.
You're welcome.
So for, I think it's the third problem. If you have a PID with a quotient field, then, so then overring is a localization
Mhm.
of R. I think I did that bit correctly, that any overring is a localization, but then the conclusion is to show that any overring of a PID is a PID. And that bit, I did not get any of that right. So,
Okay, so let's look at that real quick. So I'll pick it up from there, but if any of you guys have a problem with that, I'll work back and do the previous one as well. So.
Thank you.
You're welcome. Sure thing. So where we're at now is if you have an overring, R is PID. Okay, it's quotient field, given an overring, then it's a localization for some appropriate S. Plane. Plane is PID. Well, this end, so let J be an ideal of T. Now, one thing that'll make your life easier is using this theorem that we have, localization. So we know that J for some I R, some ideal I R. And you may have used that, I'm not sure.
no, I don't think so.
That'll make your life easier for sure. So basically what this says, is J is a set of alpha over S, where alpha is an I. Suppose that I is generated by X. Right, and this is just an ideal of R.
Okay.
And I claim J is generated by X is an ideal of the big ring.
Mhm.
That is to say, X, I'm sorry, J is X times R localized to S. So let's do our thing here. So let J be in J. And J alpha over S. Or alpha I S S. But alpha is equal to R X for some R and R. Because actually alpha flips an I, and so it can be written as an R multiple of X.
Okay. Yeah.
So J is Rx over S, which is X times R over S. So this is it. It's an R over S multiple of X.
Okay.
And that's really the hard part.
So here where you just have alphas and I, that's just from. Is that from like the definition? I guess I don't know where I comes from. Is I just what we need it to be?
It's from this theorem here. This
Okay.
correspondence theorem about ideals and localizations. Any ideal in the localization, any ideal J at R localized S is the form I localized S for some ideal I in R. And the other containment is not too bad because all we gotta do now is show that this is J. Well, and that's the other containment.
Yeah, I have no idea what that did then. I think I said if R has no non-zero divisors and 0 is not S, then RS is an integral domain. Oh, I see what I did there. Okay. I concluded that 0 wasn't in something, but I didn't know that.
I don't know what happened there. Colin, can you hear me? Give me a thumbs up. Can you hear me? Well, there we go. Try that again. I know. Let me try this. Really not there. Can you hear me now? Can you hear me now? Okay. Let's set up there. I think I must turn this on. That's this thing rolling on the board here. Okay, how about Colin, do you have anything? Yeah, you'll have to put it in the chat. Something. Well. See if we can get around this. Where's the sound is? Let me try. Let me look at this real quick. Okay, solve this. Oh, that's all the way up. Here. Well, at least you can hear me. Actually, you know what, Colin, if you can ask the question, I can, let me go fire up my other computer and join from another computer as well, one that works. Let's see. Try this. I wonder if I can join my own meeting here. Minimum 865. Kill everything. If I kill you, Colin, I'll come back and get you. Oh, there we go. Freaking game done. Okay.
Mute yourself.
I mean, you can just mute this one here. I can mute this one and then.
Okay, ask me the question. Oh, I know who this is. Okay, yeah, maybe. Oh, I can call that up. Party of the last problem on the midterm. Okay, let me see if I've got it posted online here. And I'll share it if I've got that. And if not, I'll send it to myself real quick. Okay, no problem though. I can go get it. Okay. I think I can recall this up and put it online here. We can see it because you're right. It's a little complicated. We might have to work through it a little bit. All right, so let's see if I can Share the screen. Oh, no. All right, so I'll share the screen. So did you mean part E on the last problem? Okay, right. So it was the one with all that group stuff in it, right? Right. Okay, so let's, I'll call that right up. All right, let's see here. Okay. So Colin, can you see what I've got up there on board? So here it is. I've got enough board worked out over there, yes. Let's see here. Try that. There we go. I hope you can sort of see that. Okay, so I'm gonna, for my own benefit, I'm probably gonna run through this really quick. For this problem, suppose G is a finite simple group of order 168, which is 2 cubed on 3 times 7. How many elements of order 7 does G have? So the number of 7 groups is equivalent to 1 mod 7 and divides like 24. And so it's 1 or 8. And if we're assuming it's simple, it can't be 1. So there must be 48 elements of order 7 because every one of those 8 groups contains 6 or 48 or order 7. Show that G has 8 conjugate subgroups of order 21. And so I'll think normalizer. If let's say H is C of 7 group, then number of conjugates is 1 to orbit. Under conjugation. And 168 divided by 8 is order of stabilizer, which in this case is the normalizer. So the normalizer in G of H is 21. And notice that each one of these CeLO 7 groups must contain, each one of these CeLO 7 subgroups must have a normalizer of order 21. And there has to be 8 different ones, 1 for each conjugate, because there's 8 different 7 groups that are all contained in there. So there's a 21, there's 8 of them. Number C, show that if H1 and H2 are two distinct groups of order 21, then they must intersect in a subgroup N of order 3. So C, suppose H1 and H2 are two of these subgroups. Well, let me point out that H1 intersect H2 they're both subgroups of order 21. So if you look at their intersection, it's got to be one of those four numbers. Now, what's that?
Like the order of that intersection.
Yeah, yeah. Thank you. Yeah, the order is one of these four numbers. It can't be that. And it can't be that because they're normal algebras of the distinct 7 groups. And it can't be that because if you look at the number of elements in H1, H2, I mean, as a set, this is bigger than the size of the group, right? And so that's not going to work out very well for you. So that means that any two of them must intersect in a subgroup of order 3. Okay, so let P be a CeLO 2 subgroup of G. Show that G equals PH1 and P intersect H1 is E, but G is not the semi-direct product of P and H1. Okay. Yes. And it's important here that we noted that this is a simple group. I gave you, that's the problem. So this one, P is CeLO 2 subgroup. Let's just count the number of elements here, just like we did before. I'm sure that's PH1. Yes. This is 8 times 21 over 1. Because this is part of the problem as well, but it says show that P intersect H1 is the identity, but their orders are relatively prime, so that's easy to see. So in particular, G is PH1, but it's not the semi-direct product because neither one of those pieces is normal, because we're assuming that G is a simple group, and so none of the proper subgroups P or H1 has to be normal. And finally, we get to the crux, what was asked in the first place, show that H1 is not abelian. I figured out a better way to do this. Let's see, use the facts to show that if H1 is abelian, well, let's just try to prove this hint here. Suppose H1 is abelian. Right. Oh, right. And that means that here's each. Let's see. So for a billion. Let's see. Let's see, so these are all conscious of the 21, which means right. I think I see what I'm doing here. I'm just gonna wrap my head around it. And each dot is a billion. So if one of these subgroups of 421 is a billion, then they all have to pay. Now, if there's more, that means if you take right. And let's see. And each let's see what's that's going to be 56. Okay, so how many three groups are there? Put this down. 3. Okay. 2, 4, 4 and 14. 7, 8, which is 4, 3, 4, 7. 8. And the group of 21 is the normalizer of the group of 21 is the normalizer of group of 7. So. Right, so if they're a billion, that means the normalizer. So it means that normalizer of that group of order 3 has to be at least group of order 21. It's a billion. And so its normalizer has to be group of order 21 or multiple. So the normalizer of that group of order 21. So the normalizer of 3. Group of order 21, its normalizer. What's only normal self? This is one way of looking at it. So if H1 is a billion, and normal in H1. So normalizer G for H1 contains no. So the normalizer in G of n must contain H1 at least. Which means it must be multiple of 21. And so if it's the normalizer G of n is exactly 21, that means n. Yes. Oh, no. If it's a billion, yeah. All right, I don't know why I didn't think of this earlier. Normalizer in G of n. It has to contain all of the conjugates. Because if it's well, actually H1 and H2, because it could be a different one here, but and notice that H1, H2 as a set this is what, as a set, this is going to be 21, 21 over 3, which is so let me tell you where I'm at. Here we go. I think we can answer this now. I think I'm doing this a different way. So let's suppose we're up here. Suppose H1 is a billion. Well, all the HIs, they're all the conjugates of this normalizer of the CL7 group, or CL7. So all the HIs are equal. Okay, or I'm sorry, are abelian. Right? Suppose that H1, H2 intersect in a group of order 3. Right? N. Now, H1 and H2 are both abelian. So N is normal in H1 and N is normal in H2. Correct? So N is so the normalizer in G of N contains it has to contain H1, H2. Now, I'm not claiming that's a group, but it has to contain all these elements because every element of H1 and every element of H2 normalize N. And so every one of these things has to be in there. As a set, that's going to be 100 and now, the order of the group is 168. And just this by itself, all these things have to normalize, right? Because the normalizer has to contain all of H1, the normalizer has to contain all of H2. So they have to contain all the products. So the normalizer has to be this much. Now, there is no subgroup of this size. This is just a set ostensibly. But I mean, this is bigger than half the order of the group. So the order of the normalizer in G of H, or I'm sorry, of N, is 168. That means that G is normal in this group, which is ridiculous because it's simple, right? Therefore, there's no way that the subgroup of order 21 can be abelian. It's got to be non-abelian. Does that make sense? Oh, there you are. Yeah. Does that make sense? Yeah, so right. Okay, because what happens here is, do you agree that whatever the normalizer is has to contain all of H1 and all of H2, right? So it has to contain this entire set of elements, whatever they spray out, right? But this set of elements sprays out 147 distinct elements, right? That means it can't, anything, the normalizer has to contain this set. And so the subgroup that is the normalizer has to contain this set, and it has to have at least 147 elements, right? The only way it could be a proper subgroup if it was half of this or less. Right. Oh, sure, sir. There's a lot of technology going on this piece section.
I think I have one really brief question and then one like non-math question. And then I'm good to go. But
Okay.
I'm just looking back at the notation for the localization thing. And is the S inverse I notation, is that the same as I?
So that's,
I
yes,
sub
it
S?
is.
Okay,
Yes.
okay. That's. And then my other question was, just, I realized I forgot to come to you to do the like midterm assessment thing.
We can do that right after.
Oh, okay.
Yeah.
I wasn't sure if it was,
Colin, are you good to go? Okay, all right. So did you have any more? We good?
I'm good.
Okay. I will see you at office hours if you need it. Otherwise, you guys keep between the ditches. And we can do